Hello. Hey everybody, welcome back. I'm David. I work at Cognitect, and I'm here to talk to you today about Datomic. So I'm going to be going over some basics for those of you who have no experience with Datomic, just enough context to provide context for some of the things I'll talk about later. So I'm going to talk about the information model, very high level, talk about the architecture, again, very high level, and then I'm going to get into the query and entity and pull APIs, and, well, you'll see why. So the information model. Datomic's information model is very simple. It has very small building blocks. We have a fact. I'm going to explain what all these things are for those of you who haven't seen it before. An attribute, an entity, and then the idea of an immutable database. And so a fact is a combination of entity ID, attribute, and a value for that attribute, and then the transaction when that fact was asserted into the database. So we have this idea of facts being asserted or retracted, and what that allows us to do is if the value changes in time, we can change it in the database without actually deleting that data. We just add a new fact, and we retract the old fact. But that old fact still lives in the database, and it's associated with the transaction ID when it was asserted, so we can go back in time and find the old values. I'm not going to be talking much about the time model, but that's a very important aspect of Datomic. So the way these are stored in the database is in something called a datum. And the datum has the entity ID, it has the ID of the attribute, and then the value, and then the transaction. So here in this first example, the entity ID is this really long number with 774 at the end, and the attribute is artist name. All these examples, by the way, are from the Music Brains database, which is a database of information about music that was recorded. We have a small example subset of that we use for Datomic examples a lot, from 1968 to 1973. So all of these examples are going to be musicians that maybe you've never heard of, but that's not that important to understand the concepts. So an entity. An entity is a collection of facts that have the same entity ID. Now, if you look at this collection of facts, you can see that all of the attributes, except for the first one, they're all namespaced keywords with artist at the beginning. Now, this is purely for readability. There's no programmatic binding between these things. There's no table with columns that says there's a name column and a type column and a gender column. And we just assemble them together in an entity. And you can have other entities that represent artists that have a different set of attributes, and that's perfectly fine, and you'll still be able to query for things. For example, this entity, Wes Montgomery, is a person, and so this person has a gender attribute. You can also have a group, and the gender attribute may or may not make sense in that context. So you don't have to have all of the attributes for the entity to be complete. Also, if you had different kinds of people in the data model, instead of artist name, it might be person name, and that would fit perfectly fine within this entity. Here's another view of the same entity. This one looks a little more familiar. It's Eden, regular Eden map, Clojure map. And so another important building block is the fact that attributes themselves are entities, and they're represented in the database in the same way as any other entity is. This is the artist name attribute. It's got a value type of string. There are obviously different value types that we can have. It has cardinality of 1. We can have cardinality 1 or many. And if we have cardinality many, and we have a many-to-many situation, we don't have to do the kind of thing we have to do in a relational database where you have like a join table. We just declare that it's cardinality many, and Datomic will take care of that relationship for us. Here's a fun attribute. This is the dbident attribute. And that's actually what it looks like in the database. And you can see that the dbident attribute of the dbident attribute is dbident. So this whole idea goes way down to the bottom. It's turtles all the way down. So, and then the thing I didn't really talk about yet is just the idea of a database. So when you're querying against a database, and a database in Datomic is an immutable view of the data at a particular point in time. So if you ask for a database right now, it's going to give you the latest view of that data. And as novelty comes into the database, your database that you have in hand right now is not going to change at all. So you can query, you can run long analytics processes on it, and you don't have to try to coordinate with the data that's flowing in at the same time. All right. So very high level again, the architecture, Datomic's architecture is a little different from traditional architectures. What we're accustomed to seeing is that all of the activities that are managed by a database, transaction, indexing, query, stored procedures, those things all happen in one process. And over time, as databases grow larger, we've come up with ways to have redundant processes and kind of split the responsibilities across, and then we end up with concepts like eventual consistency and whatnot. Datomic breaks this mold by splitting those activities into separate processes. So we've got one process that manages transaction, putting data into the database, indexing. Storage is not part of Datomic. The transactor puts data into any of various storage systems that you may want to use. And then query happens in your application's process. And we're able to do that, Datomic's able to do that because it maintains a local cache of the data. So as you query, when you have a cold cache, there's going to be a request that goes out to storage to pull back data segments, and data segments are big collections of datums. And once they're there in memory, and then you can continue to query against those same datums, and you never have to go back to storage for those. And so if you live in a world where your application, your database is actually small enough to fit in memory, the cache heats up, gets the whole database in there, and there's zero network communication after that. In cases which are common as well, where the whole database won't fit in memory, Datomic has a least recently used algorithm for invalidating the cache and bringing in new data. But the overriding point here is that when you do queries, you're doing queries experientially, like as a developer, as you're writing, and what actually happens a large portion of the time is that you're querying against data that's already in memory. You don't have to go across the network to get it. And that changes the kinds of things that we can do. So moving on to query. Datomic uses Datalog as its query language. And Datalog is a data-oriented query language. We're not dealing with strings like we do with SQL. So that gives us a lot of advantages. First of all, this is just a normal Clojure data structure. It's got symbols, it's got keywords, it's got vectors. And if we want to compose these things, we don't need to do string concatenation to compose these things. And it's very evident what it is we're trying to do here. I'll explain this for those of you who haven't seen it. This is a very simple example. We're saying we want to find any symbol with a question mark at the beginning as a variable. So we want to find all of the values for the variable e that fit into this pattern, and the pattern is the vector at the bottom of e, artist country, and artist Spain. So we're saying, let's find all of the Spanish artists that are in the database here, and just get their entity IDs. And so remember before when I showed you the facts, they go in the order entity, attribute, value, and then transaction, and then whether they were added or retracted. So in this case, we've only got 3 of those parts. We've got the entity, the attribute, and the value. The attribute and the value are values that we've put there, constants. We know what they are. So the only thing we're trying to solve for is what are the potential values of e. You could put variables in any of those positions. In this example, though, we're just looking for the values of e. And so the query engine is going to look through the datums. It's going to find datums that have artist country and country Spain in the attribute and value positions. It's going to grab their entity IDs, and that's what it's going to return to you. And you could see the way these are returned It's a collection of tuples, one tuples in this case, because we only asked for one variable to be filled in. So in a case where you're just looking for one, you might not want to have to unpack the tuples, and so you can ask for just a collection of these values. So what we're saying here with the vector of E and ellipses is find me a collection of values, return me the collection of values of E that fit into this pattern. So now we just get a nice list of those. So asking about one data pattern is nice, but we probably want to refine the query a little bit more. So here's an example where we could say, specifically, we want the Spanish groups that are, the Spanish artists that are groups. And so what happens here is the query engine processes the first data pattern first, right? So first it's going to look for all the values of E that fit into the pattern with artist, country, and country Spain. And then it's going to narrow that down further to all the values of E that also fit into the pattern of variable E, artist type, and artist type group. This is an important thing. The order matters. So what you want is for each of your data patterns to be, you want the most restrictive ones at the top because that's going to get processed first. And so in this particular data set, there are 58 Spanish artists, but there are over 2,000 groups. And so it makes much more sense to narrow the space of possible values down to 58 first, and then work within those for the second part of the query, than the other way around. So far we've only talked about looking at different attributes of the same entity. This is how you express a join in Datalog. We're going to join against different entities, across different entities. So we're binding values to the E variable in the first expression that satisfy that, narrowing those values down further in the second expression. And then on the third line, you could see that the variable E is in the third position, in the value position. And that's how we do a join. We don't have to have any special syntax for this, because all we're doing is we're filling in those values with the combination, filling in the variables rather, with the combination of values that satisfy all of the data patterns in the query. So this would give us all the groups from Spain with releases in 1970. We can bind the releases to different variables in order to have, in order to be able to say something like, give me all the groups with releases in 1970 and 71. And you can see we've got R1 and R2, and you can see how those get narrowed down to 1970 and 1971. And as we constrain the possible values for those variables, we're also constraining the possible values for E at the same time, even though we're only asking for the E's in this case. All right. A recent addition is an explicit OR. So for those of you who've worked with Datomic for a while, you know that you can do an implicit OR using rules. I'm not going to be talking about rules today, but just briefly, rules are ways of composing data patterns into a named rule that you can then plug into a query so that you can reuse them. And they also provide the benefit of an implicit OR. Well, now we have an explicit OR. So here we can say, it's, I want the releases in 1970 or 1971. There are other ways to express the same thing, but we now have this at our disposal. There's also OR join, which lets us do something a little more complicated. So Paco de Lucia, who is a guitar player who's well known outside of Spain, or at least he used to be. I don't know how well known he is today, but he played on some records where he just played on a track, but he wasn't listed as the artist on the record, potentially. And he also played on some records where he's listed as the artist on the record. And so this query allows us to find any release that has Paco de Lucia listed as an artist on the release or as an artist on any of the tracks. And we use OR join for that because we want to scope we want to join explicitly on the R variable and the A variable. And we don't want to care outside of the join expression about the M and T variables. We've got now negations. So this is new. It came in January. So it used to be that if you wanted to find the Spanish artists that aren't in groups, you'd have to get all of the Spanish artists, and then you'd have to filter out the ones that were of different types. And now we have an explicit not expression so that you can do this very declaratively. And similar to the or join, we've also got not join, which lets us have effectively a subquery that says we want to exclude all of the values for let's see, we're joining on E, right? The values for E where we didn't have releases in both 1970 and 1971, but we had one or the other. So there's a lot of more features that I'm not going to cover. I mentioned composable rules. You can also have expression clauses, predicates, so you could say, you can actually use what looks like a Clojure function and say, give me all the values of the year that are less than a certain year, this sort of thing. We have aggregates, so you can get counts of different variables, min, max, etc. But what I want to move on to now is entity. All of the examples that I showed you, we were just pulling the entity IDs. Now, you can also pull other variables, and I'll show you some examples of that as we go on. But for right now, I'm just going to move on to entity. So, entity is a function. It takes a database. And remember, a database means an immutable snapshot, an immutable view of the data at a particular point in time. And you give it an entity identifier. And an entity ID can be any of the numeric IDs that we've been looking at. There's a concept of a lookup ref, and a lookup ref is a vector of an attribute and a value, and that attribute has to be declared unique when you create that attribute, when you assert it into the database as an entity. And then you can use that unique value to look up an entity as well. Also, the DB idents, which are also unique throughout the system. So you can use any of those three. And when you call this function, you get back something that looks like a map. And in this case, it's presenting itself as it's got the one key, DBID, and the value that we passed in. Now, what that actually is it's not a regular Clojure map. It's a Datomic entity map. And so an entity map is associative like a map. You can ask it about its keys. It's lazy, so it doesn't have all its information right away, but as you ask for information, it loads it. And this is where Datomic's architecture, having all the data here in memory, supports something like this, where we can ask for the entity ID, and then we can go back and ask for more information. And there's a really, really good chance that when we got the entity ID and the data segments that we pulled back have that entity ID in it, they also have all of the other attributes of that same entity. So we're not having to go over the network the way we would if we were using a client-server model with any other kind of database. The other thing about entity maps is that they're navigational, and I'll explain what I mean by that in a minute. So they're associative, so you can say, give me the artist's name, and it loads that up. And an interesting thing about this, well, I skipped ahead there for a second. So you can ask it for all of its keys, the way you would a map. So now if we were to def that entity to a var named Booker T, and then we looked at the value of that var, we'd see it's just got DBID. That's all that it's got loaded right now. Now, if we were then to ask it for the artist's name, we'd get that value back from that function. But also, if we look back at the entity, it now has artist's name loaded into it. So it loads these things in, and they're available. You can ask for them anytime, but they're actually not loaded into the object until you ask for them. There's a touch function which says, get me all of the attributes and their values all in one go. This is something you may or may not want to do, because if you do it with an entity that sits at the top of a deep graph, you're going to be pulling back a lot of data all at once that you may or may not care about. So one of the things you can do with attributes is you can say, you can declare that this attribute is a component of its entity. So, for example, here is a release, Samba na Madrugada, and this release has various media. It was released possibly on tape, on vinyl. This is all before the days of digital. And then each medium has tracks. And so you can see that when we touch the entity and ask for all of its information, it automatically pulls back anything that's a component of it. So the release contains all its media, each medium contains all its tracks. That all comes back at once. In terms of navigation, remember, we don't have a Clojure map in hand, we have this entity map. And so we can def it to a var in this example and ask for its name. We can also ask it for other entities that are associated with it. So in this case, we're asking for all of its releases. And when we get those back, you can see that the releases are similar representations to what we saw before. It looks like a map with a DB ID in it. But if you were to map over that with the artist name keyword, we'd get back the artist names for all of those. So we're navigating from one entity to the other entity in that way. And we don't have to pull all of that data back at once. So let's say that we def the first of those artists to a var, Paulinho da Viola. And so he's got a DB ID, and the artist name shows up because in the previous example, I asked for its artist name, and so it loaded up into that entity. And that's why we see it here when we do this def. Then we can navigate, and notice now the underscore in release underscore artists. So what we're actually doing is we're navigating from the artist to all the releases that have that artist as an attribute for release artists. And so you could see that returns us a bunch of releases. Maybe you can't see that. Well, you can, because then we go through, iterate through their names and map over their names, and we have all the names of the different releases. So you can navigate in either direction. And this is actually a really interesting thing about Datomic's design, because to do that sort of bidirectional navigation, you have to do some tricky things in other databases. So the entity API, it's associative, it's lazy, bidirectionally navigational, and the fact that the data here, the data is in memory, means that it's okay to get the entity IDs, go get an entity, and start asking questions about it, and you don't have anywhere near the chatter, and maybe no chatter at all, that you do in a traditional client-server model. Okay, so the next thing I want to talk about is the pull API. Pull was introduced late last year, and pull has some similarities with entity. We can use it, given an entity ID and a data pattern in a database, we can get information about that entity. The entity ID, just like the entity function, the entity ID can be numeric, a lookup ref, or the ident. So if we were to use the wildcard specification, which is just a star, we're going to get back all of the values associated with that entity. But this is different from the entity object. I realize I'm using the word entity in two different ways. So there's the conceptual entity, which is the collection of facts with the same entity ID, and there's the entity map that we got from the entity function. That's fun. So the thing is that this entity is just a plain old Clojure map. And so, for example, the artist type, whose value is a map of DB ID and then a number, we can't take that and then navigate using it. We can't ask it for any of the other attributes of the artist type. It's just a map. And we can use that ID to go back and ask for that entity if we want it. But that's a fundamental difference between this and the entity. As with entity, if we were to use the wildcard, it would pull back all of the data for the entire graph if it has any component entities. So here again, we've got a release which owns media, and each medium owns tracks, and we get all of that data. Again, though, we're still getting these maps of dBi data to a numeric value that aren't going to help us right now very much. So I'll talk about that more in a minute. Well, I'll talk about it now. So what we can do is we can specify the attributes that we want, and we can do this at any level. So at the top level, we can say, all I want is the artist name. And so here, the vector of artist name, that is our data pattern. That's our pull pattern. And we're saying this is the structure that I'm looking for. And that gives us back a map with the key artist name and the value associated with it. We can ask for more than one thing. We can say, give me the artist name and the artist country. So in this case, we've got a map of artist name pointing to the value, and then we've got artist country pointing to this map. And again, the map, dBid with a value, isn't that helpful. So what we can do is we can specify how we want artist country to be returned, and we do that with a map specification. So here in the second example, we've replaced the keyword artist country with a map that's got a key artist country, and then that key points to the specification for how we want to render artist country. And we say we want the country name in that case. And in this example, you can start to see the beauty of this API because the specification, artist name, and then the map of artist country pointing to country name, the results look exactly like that. So if you're looking at some code and trying to understand what it's going to give back to you, this is exactly what you're going to get, which is very different from when you're pulling back values using query and then cobbling them together into some data structure that you're looking for. You can combine wildcards and these map specifications. So in this example, we're saying, I want all of the attributes, but I want to specifically for artist type, artist gender, and artist country, here are the specifications for how I want those rendered. So this gives us something a little more useful. For the artist type, we're getting back the dB ident. For the artist country, we happen in the data model, we happen to have string names, country names, so we're pulling those back because that's even more readable. And then these can nest arbitrarily. So in the case of a release which has media, each of which has tracks, we can use this specification to say, okay, I want the names of the media, I want the names of the tracks, and I don't want any other information. And then, like entity, you can navigate in reverse. So by putting an underscore in front of the second half of the attribute name, we can find the other attribute, the other entities that own this one, or that have this one as an attribute. So here we're saying, give me all of the tracks that have Elise Regina listed as an artist on that track. But the structure that we presented in is Elise Regina pointing to all of the tracks that she was on. So pull has a bunch of other features that I'm not going to have time to go into today, but you can do limit expressions. So sometimes you have an attribute that's cardinality many that has more than you want right now. And so you can, there's a way to say I only want 5, 10, whatever of those. Default expressions, so you can say, well, if it doesn't have this attribute, give me back this default value so I can put that, you'll put it in the map for me. So the map that I'm getting back has all the data in it that I want. You can have, like if you have friends of friends of friends kind of scenario, you can stop the recursion of that at a certain point so that you don't gobble up the entire graph in one go. And there's more that I won't go into right now, but what I want to move on to is combining pull and query. So far, what I showed before was, you could query for just the entity IDs, and then you could use the entity API or the pull API to then flesh them out. Well, it turns out that you could do the same thing in one function call. And so this is not an example of that. This is just to set that up. So before, if we wanted to get all the names of the artists that are groups from Spain, we would do something like this. And notice the third pattern in this query, it's only there to give us back values of the variable n. It's not really, the entities that we're searching for are these groups, right? So if you can think of the where clause as search, what I'm searching for, a nice way then to express the details is using the pull, using a pull expression right in query, which is supported. So here, the query is much more definitive about the kinds of entities that I'm looking for, and separate in the pull is the specific information that I want. And so what's really nice about that is that you can compose these things. So you can have a bunch of different queries that narrow down the space of entities that you're interested in, separate from the way you want to render the data in those queries. So you can have different contexts where you need different data. And it makes the whole thing much more composable. And similar to what we were seeing before, the pull expression is a very strong indicator of the data, what the data is going to look like that you get back. And just for comparison, here we're pulling back the artist name and then the release names of all the releases that each artist was in. To do that, to get this data structure, if we were just using query, we would do something like this. I'm not going to go into the detail about it, but you can see that it's nowhere near as obvious what's going on here, because there's a bunch of post-processing that we have to do to the query results. And similarly, if we were to start navigating through the entity API, we can have a smaller query here, but still it's a lot less obvious the data that we're actually going to get back. And compare both of those to this example, where looking at the pull expression, it's just completely evident, completely clear. So in summary, data here in the same process enables us to separate query from either entity or the pull APIs. And so, you can certainly do that, what I showed you. You can certainly get everything that you want in query, but separating these things out, decoupling them, is a very nice way to organize your programs. So you can use query just to get the entities. You can use entity to get lazy navigational access to the detail, or you can use pull for context-specific eager access to the detail. And then you can also use pull right inside your query, which is something you can't do with the entity API. And it gives you all the expressiveness and power of all of those things combined in a single API call. And that is all I've got. So I don't know how I'm doing on time. It looks like I have 10 minutes. So I've got we've got lunch coming up, so we don't have to take all 10 minutes. But if you have any questions, now's the time.